Today I'm going to talk about an idea that we've had and that we've been working on to really take advantage of the advances in AI to contribute to solving the UN Sustainable Development Goals. We've been working on a project at Spark Beyond that leverages the state-of-the-art NLP with modern web resources, and I hope to convince you today that using these tools and building a nice interface will help bridge the gap between evidence and policy. So our mission at Spark Beyond is to harness humanity's collective intelligence to solve the world's most complex challenges. When we really say this, we're talking about some of the work that we've done thus far, which currently includes generating greater than $1 billion in impact for a lot of companies, including the Fortune 500 companies. We've done this by generating a lot of hypotheses, indexing patents, research publications, exploring previous innovations, and things like that. But today, I'm actually going to talk about some other things. So one, we've also done some social good. So we've worked on projects looking for novel drivers on optimizing affordable housing, advancing cancer research, and reducing prison violence. But today I'm going to talk in specific about how this applies to the UN Sustainable Development Goals. And so I want to start by talking about some of the challenges that we face in achieving these goals. For one, these goals involve some highly interdisciplinary research. It requires information from disparate groups of researchers. For two, as humans, we're inherently limited by cognitive bottlenecks, our cognitive bias, and also things like our capacity to read all the research as it comes out. So at the current rate that research has been coming out, it's pretty difficult for one individual to catch up on everything that's new. And we may have some assumptions that hold true, but in today's dynamic world, those assumptions may lose their predictive power over time. Furthermore, we typically assume that AI is going to involve a lot of data. And it's often the case that our most marginalized populations or the more remote communities are underrepresented in our data. So what is the proposal I have to overcome these challenges? My suggestion is that we're going to use a web knowledge mining tool to help us resolve these. This will allow us to bridge the gap between data and policymakers. It'll allow us to enable open innovation through crowdsourcing. We can connect to previously unconnected dots by mining knowledges from billions of scientific articles and publications. We are able to rank those sources according to their credibility and evidence amount. And it allows us to learn from the past 100 years of inventions to synthesize breakthroughs at scale. So what does this really mean? We've built this sort of problem-solving platform that essentially ingests these things like patents and research publications and news. And we mine that using these NLP tools to explore things that are relevant, what has momentum, what activities are happening, to search for unmet needs, and to innovate. And what does this look like in action? So we had partnered for a while and are currently partnering with XPRIZE, and they were working on a project hoping to feed the next billion via sustainable agriculture. This prize itself is in alignment with two of the goals: to alleviate hunger and for responsible consumption and production of food. And I'm going to talk you through some ideas about how this might be done. So as a researcher, you might start with something like a Google search. And if you did that, you would notice that searching for sustainable agriculture will give you 240 million results. In order to synthesize this, you would probably get, some answers to problems that we might be facing, but it's going to require you to do a lot of digging, searching through all of these possible results. So what I'm suggesting is that we use AI to help us with this problem. So just like Google, in our tool, the new platform that we're developing, users can enter a search term, and then from this search term, they're allowed to search for various queries or relationships. So in this case, for sustainable agriculture, I'm looking at things that negatively influence it. This query is then run through Google Search's API and Bing for a whole web search. It can also pick out research articles, including millions of articles that we've indexed from PubMed, patents as registered by the US Patents Office, and an indexed news source. So once it does that, we use a BERT-based question and answer system to determine what concepts are listed as possible targets to the query. And we present them to the users as list of evidences, sorted by the number and strength of those results. You can click on these evidences and actually see the original sources. You can add additional sources if you have some. And this becomes a living document that can be curated, shared, and explored. We also built a GeoView, which allows you to see where each of these things take place in the world. So the information here comes from individual sources, and those sources themselves are mined for their text. And the design of this tool also allows for further research into any node. For example, I might want to know something about how we can decrease low yield, so increase yield. And I might want to know what are some of the deficiencies of these possible solutions. So again, I can click on this and do my same research. I can send a query. And what I wind up is an expanded flow that now includes some of these possible solutions and some of the deficiencies of those solutions. So in this case, fertilizer can help me with my yields, but it also has these following deficiencies. I can also look at these individual nodes themselves. So for example, I can dig into fertilizer. I'm able to look at what are the trend momentums in fertilizers in the news, patents, publications, et cetera. I can see who's got the top patent assignees for fertilizers, and I can even track something about the market size that is being used for this particular topic, so fertilizers. If I have access to data, I can also use this data to build a machine learning model. And in this case, I have something like countries, time, and usage of different fertilizers. If I also have the same information about different countries across time and their yield, I can build a model. And basically, we wind up with something like this. It shows us a model score. We can click on it, and we get something that looks like this, which is our usual platform at Spark Beyond, giving us some features. For example, how much nitrogen usage over the last 20 years can actually result in a higher yield. So that's pretty cool. There are a whole bunch of other really neat things that I can show you, but I'm running out of time, so I'm going to sort of go through them quickly. We also have this possibility of looking for things that are related to one another and generating a bunch of different questions or innovations and sending that information out to experts. So if you have a group of experts who you know a lot about a topic, you can generate a series of questions and send them to them. So here's an example of a list of questions that were generated by our platform. They get sent to different users that look like this. So can you think of an invention inspired by utilizing multi-level composition of plants? The users respond to this, and then what we wind up getting is a summary of those responses. So for example, people are now saying, let's invent vertical farming. So this is great. Now we've had like a real whirlwind of this new product, aimed to take advantages of new advances in natural language processing. What I hope I have conveyed is how these kinds of tools can help us accelerate research. It also allows us to visually present that information and help us bring that information in an easy to ingest and explorable way, allowing for the possibility of giving researchers new tools, as well as a new possible way of conveying findings to policymakers. And I'm going to end this presentation with a quick video that was made with XPRIZE and Microsoft.
XPRIZE is a nonprofit, social impact organization of people working to solve the world's grand challenges and accelerate abundance for all. We're currently tackling carbon emission, zero waste mining, the future of forest, and sustainability in general. We do that through designing and operating competitions that stimulate and incentivize the crowd to accelerate technology and science to solve those grand challenges. Crowds and crowdsourcing, by definition, produce huge quantities of data and insights.
Spark Beyond began as a result of a radical experiment where we wanted to see whether we can decipher the code of innovation, of inventiveness, by understanding the building blocks, the Lego bricks that allow us to compose them and create new ideas.
So when we think about all of the pressing issues that we face as a society, we can no longer afford to wait for the next individual to have their sort of aha moment. We want to crowdsource the aha moment to the masses. The research studio that we have is really kind of like having your AI sidekick. What it does is basically allows a human researcher to unlock the power of all of the knowledge that's out there. So if the researcher wants to know what is causing a particular problem, the engine goes out, reads all the information, distills the most relevant information, and helps build a knowledge graph that explains that.
The future of research is about bringing machines and humans, expedite the pace in which research is done, but also tapping into way larger quantities of information that previously were untapped. This information has the potential to inform us of important steps and solutions to some of the world's grand challenges. This collaboration with Spark Beyond will lead to more data, faster analysis, and better insights.
I believe that social responsibility should be part of our DNA, of who we are as human beings.
A synergy between humans and machines can overcome and solve the most important challenges.
And I believe that AI equipped us with an unparalleled opportunity to do social impact at scale that we as humans never were able to experience before.
We need everyone, everywhere. It will take all of us. And we have to do it now before it's too late.
we're going to see some tremendous developments, from cancer research to climate issues to deforestation to food, water, everything. It's no longer far-fetched dreams. This is going to happen in our lifetime.
Thanks, everyone.
Hello, everybody. My name is Eric Kingery. I'm the VP of Engineering at Public Good Software. This is Stephen Brown. He worked with us as an ML engineer this summer, and he's a researcher at the New York Institute of Technology. We're going to talk about using data science to facilitate civic action today. That was our paper. And at Public Good, we employ data science and machine learning to make the news actionable. We do that by matching news articles to social causes, providing readers an opportunity to make a positive impact through actions, including fundraising, advocacy, and education. And we not only empower individual consumers, but in aggregate, we provide data to the Gates Foundation, for example, so they can research and analyze trends and the ways in which people want to take action on news specifically. So here's what that looks like. A media partner of ours is WGN-TV in Chicago, and they have an article about someone who gave a bunch of found money to a food bank. So we were able to analyze that article and relate it to Unilever's Right to Shower campaign so that people who are reading it can learn more about how they can help people in this specific case learn more about Unilever's efforts to provide showers to people who don't have access to them. We were fortunate enough to present here 2 years ago, and we were in phase 2. We were just about to embark on phase 2. So today we're going to talk about what we've learned since then and a little more about our current innovation, which we call similarity modeling, which is using transfer learning with BERT to create cause-specific models as opposed to part of the 37-class taxonomy. So at Public Good, we use taxonomy to facilitate civic action. And in every machine learning effort, there's a critical juncture where you need to apply machine learning algorithms to your specific domain. So that process for us began as we developed this custom taxonomy. So looking at something like the UN Sustainable Development Goals was really helpful for us as a start. And we can look at SDG number 10 for an example, reducing inequalities. What we found was if you just throw together thousands of news articles focused on reducing inequalities, we weren't able to get language that was distinct enough to accurately classify those articles when they showed up in the news. But by breaking them down into 4 more specific categories, we were able to come up with a distinct set of language that allowed accurate classification and captured the majority of articles regarding reduced inequalities that were actually showing up in the news. So that process of using frameworks and taxonomies such as the UN Sustainability Goals, there are other cause taxonomies out there that we looked at, and news taxonomies. So that was really key to the start of our machine learning journey as we were developing a classifier that actually allows us to take the news and serve relevant causes, identify and serve relevant causes and opportunities for people to take action. So with our custom taxonomy in place, we built a platform around that, and this is what our previous paper is mostly about. Today we're going to focus on these similarity models. So I'll talk a little bit about those and what that means. Yeah, so what we discovered in developing the rules in the taxonomy classifier was that even the 37 classes that we came up with, 27 of which were cause-oriented, that was not necessarily sufficient to describe what was happening in the real world. So these similarity models allow us to tailor classifications that are specific to a single cause. So we can now create a more fluid taxonomy that captures some of the nuance of a cause as it relates to current events. So it's moving beyond a fixed taxonomy to a more dynamic way of classifying news articles as they appear and as the news evolves. And Stephan did an excellent job this summer helping develop some of these similarity models for us, trained them and deployed them all in one summer, and he's going to talk a little bit more about our usage of those.
Hi. So one of the big limitations that we face when we're building these kinds of models is access to training data. So under that sort of constraint, we first looked at transfer learning. And for those of you who don't know what transfer learning is when you take a pre-trained neural network for general tasks and then fine-tune that neural network for your domain-specific task. Doing this has allowed a lot of smaller organizations that don't have access to training data to sort of replicate state-of-the-art results on their domain-specific tasks. So when we did this, we first looked at BERT, actually. BERT came out in December of 2018. It is Google's new bidirectional encoding representations for transformers model. It has achieved state-of-the-art results on over 11 different natural language processing tasks, and we used it for multi-label text classification. So we were able to take BERT's 24-layer neural network for also perspective. Most neural networks that were used for pre-training up until the past 2 years were 6 layers was considered big. So 24-layer neural network is massive. This thing was trained on all of Wikipedia and a lot of books corpus data using just plain text. And we were able to take it and just train 1 layer to achieve state-of-the-art performance on classifying these news articles. We were able to achieve 95% accuracy with our first model, which was for climate change. So that was one of the better things about BERT. Another good thing about BERT is that it's contextual. So the great thing about being bidirectional is that it captures both the first word and the previous word and the next word following that in the word embedding. So it can actually tell the difference between if you're talking about Python the language or Python the snake. I was attacked by a python. BERT is going to know that you're talking about a snake and not coding. Well, maybe. So that was sort of what I focused on this summer, is creating a general framework for building these models very quickly. Because we're only training 1 layer of this 24-layer neural network, we were able to train these models within an hour or so each time. The computational expense required is large, but not unsustainable.
Thank you, Stephen. And previous to that, we had looked at GenSim, and we scored about 82% accuracy, which in a 2-class classifier above 50% is not sufficient for our purposes. But BERT is very promising and is in production right now and is scoring similar to what we saw in the test runs. So in summary, at PGS we employ data science to make the news actionable. And while our products evolved from manual placement on specific individual articles through this automated workflow, we do still integrate humans into high leverage situations on our platform. While our product evolves, our goal remains the same, revolutionizing the way consumers, nonprofits, and brands interact with media, specifically news media, to make a positive social impact on our world. I would like to thank Stephan for helping the presentation. He co-wrote the paper with us, as well as our data advisor, Q McCollum, who couldn't be here today, and our CEO, Dan's here as well, who without his insight and interest in machine learning, we probably wouldn't be doing that at Public Good. So thanks to you all. Thanks for your time.
Hey everyone, thank you so much for sticking around. I'm here to talk about kind of the mapping revolution as we see it from kind of the perspective of a private company working with humanitarian organizations as well as other tech companies to try and leverage the power of artificial intelligence to really extract very large scale data sets. We're talking data sets on the order of country scale, and then actually ingesting them into open data platforms so that various folks, various groups and communities can leverage that data for their work. So I'll specifically be talking about Humanitarian OpenStreetMap and Grand Challenges Canada. So quick raise of hands, how many people know about HOT, Humanitarian OpenStreetMap? Minimal, okay. And how many folks know about OSM, OpenStreetMap? All right, some more folks. So Humanitarian OpenStreetMap is basically, I would say, like a quick action committee that will basically help to focus resources, focus mapathons when a certain kind of humanitarian or natural crisis event has occurred. So for this instance, we're going to be talking about the ongoing Ebola crisis that's still occurring within DRC. So to kind of go back in time just a little bit, kind of one of the driving forces of OpenStreetMap is the fact that there's millions and millions of people who are just not mapped at all. So they're unknown to government agencies, they're unknown to humanitarian agencies, and so part of the goal of OpenStreetMap and HOT is to kind of decrease the data gap and to try and provide kind of a more open sense of where people live, how do we get to them, how can we improve their lives. So a really great example of this work was unfortunately focused around the 2014 Ebola outbreak that was occurring in West Africa. So that was still to date the largest Ebola outbreak that the world has seen. And basically what happened is Humanitarian OpenStreetMap said, okay, we need to do a lot of mapping very quickly. Our folks on the ground don't know where people live. They don't know the road networks to be able to gain access to them. They don't know if medical facilities are open in these remote villages. We don't know if they have access to clean water. All of these different kind of data points that directly influence kind of how bad an outbreak's gonna be, how quickly can we address the issues to hopefully stop the spread. So in 2 weeks, 2,000 different volunteers traveled to over 2,000 different villages. And basically they were asking kind of those questions that you can't necessarily discern from a satellite image. So they're trying to find out how many people live in a home, how many of those folks are literate, is there access to water close by, do they need to go travel a large distance to get it? And so I think one of the really important quotes that came out of this and out of this great work was from Doctors Without Borders. I think mapping is our single most successful example of where we are harnessing technology for the benefit of our patients. So how does Maxar play into this? Maxar, the company that I work for, we used to be known as Digital Globe. Raise of hands who knows Digital Globe. A few, my brother does. So we are a satellite imaging company. We own and operate a number of very high resolution satellites. And so the big difference with kind of commercial satellites when you compare it to federal assets like Landsat, MODIS, kind of these open and free data sets is that our imagery is a lot more resolute. So our imagery is 30 to 50 centimeters. What that means is that you can extract really finite features on the ground. And so what kind of this whole talk is supposed to be about is how do we better leverage the time of volunteers who are contributing their open time to say, I want to help to map XYZ community for this purpose. How can we maximize it so they're not drawing boxes over all of the things that are buildings? They're actually saying, back to the thing I was talking about, attributing information of, is there electricity at this home? Is there running water at this home? The features that you can't necessarily discern from satellites. So this is an image on the screen right up here. This is one of our satellite images. And all of these blue little blobs, these are all the buildings that we've extracted from our satellite imagery. And so it used to be that it would take a community of mappers several months to map on the order of a few 100,000 buildings. It's very dependent on the amount of time the folks have to contribute to it. But in essence, what we're now able to do with our partner Ecopia, we can extract 40 million buildings in a single month. And those buildings are incredibly accurate, 95% accuracy basically in terms of false positive, false negative. But what this does is it means that we can take kind of the more mindless, the less expert required mapping duties away from the volunteers, and we can give them large data sets to say, okay, now please use your local knowledge to make this a much more useful and impactful data set. And I would like to say, I mean, one of the big problems here, especially within the OSM community, is folks are a little scared and worried about taking these computer-produced data sets and ingesting them kind of freely into this tool, OSM. Because folks aren't necessarily sure, are we actually making sure that it's as accurate as we say? So we kind of have this great problem of how do we start to ingest gigabytes and terabytes worth of vector data that otherwise would have taken literally years to create. So to get into the actual core issue, this graph right here shows basically the amount of confirmed and probable cases of Ebola within various districts within the DRC. So this has been ongoing. The crisis has been ongoing since July 2018. Unfortunately, 3,000, we're now over 3,000 confirmed cases with over 2,000 confirmed deaths as a result. And as you can unfortunately see, we have a lot of uptick seen basically in April and May of this last year. So although it may not be in the news media as much as kind of people as it used to be a few months ago, the problem is actually worse, than it was, I would say, when it initially kind of came to be, at least in the mainstream media. So, the big problem here is that mapping where people live in DRC is, of course, incredibly essential so that we can start to inform Doctors Without Borders and the Red Cross and these other groups about what type of infrastructure is in these communities to help to, stem the spread of the disease. So that's kind of focus one, is the DRC. Focus two is definitely Uganda, in the sense that many millions of people are currently in the midst of fleeing the DRC as a result of this ongoing issue. And so Uganda, unfortunately, in this border region on the eastern border of DRC, there's not great infrastructure. And so a lot of these folks are basically within informal settlements. And of course, in many informal settlements, there's no access to electricity and running water and all of these things that make the spread of disease increase drastically. And so ahead of time, basically, the Uganda's Ebola National Task Force, which is kind of a grouping of the Ministry of Health, the CDC, Doctors Without Borders, IOM, a few different groups, they basically said, we really need help. We really need to map an incredible area very fast, and we need to do it, in these two different countries. So our solution is going to be focused around mapping roughly 160,000 square kilometers worth of area. And so what we're going to do is extract all of the different buildings that fall within that, and then the OSM team, in concert with Microsoft, Facebook, and some other groups, they developed what's called the ML Enabler. And the ML Enabler, from kind of the outset, the main goal is for this to start to allow users who are not necessarily tech savvy to the extent that they're writing ML algorithms, but they understand kind of what those algorithms output. The ML Enabler is supposed to be a registry of all of these different types of ML tools, and kind of discussed and presented in a way that allows those of us that aren't coders but still technically proficient to use those algorithms and say, maybe I can start to extract new data sets, new features, within this tool directly in OSM, on the open data that we already have. So that's kind of the largest goal with the ML Enabler, but a very important secondary goal is developing this pipeline, this pathway to be able to ingest data sets on the order of what we're talking about. We're going to be mapping an area that's home to roughly 5 million people. So we're not going to have, probably over 1 million buildings, but it's likely going to be 500 to 600, 700,000 buildings that we're going to ingest. And so I guess, to kind of wrap things up, I think one of the important things to think about is that this isn't a replacement for volunteer communities. We're not saying that, the data that folks have ingested into OSM isn't great. What we're saying is, let's take time, let's make sure we maximize your time when you're choosing to be a volunteer in one of these campaigns. And let's allow you to actually tell us the information that we can't yet decipher from satellites, but is still greatly gonna impact the work being done on the ground. So thank you, everybody. I really appreciate the time, so thank you very much.